This is 26.1. Enabling efficient and scalable DRAM Disturbance Mitigation via experimental exercise in modern DRAM chips. I'm happy to share a brief summary of the works that I did during my PhD. So I'll start my talk with the concept of memory isolation. Memory isolation is a principle dictating that a memory access should not have unintended side effects on data stored in other addresses. And this is a fundamental property for system robustness in terms of safety, security, and reliability. Imagine that we do not have this principle. You perform an access to a memory location, and you observe a change, a bit flip in another memory address. And we wouldn't want this because it could lead to data loss or corruption. It can compromise our application correctness. It can be used to leak your private information or even to take over your computer. Unfortunately, today memory isolation is difficult when we use our modern memory chips, and here is why. Prevalent memory technology today is dynamic random access memory, or in short DRAM. DRAM stores data in the form of electrical charge and a capacitor, and it's a volatile memory technology, so it leaks charge over time and lose data. To avoid that, we need to periodically refresh it. And unfortunately, there is this concept, phenomenon called DRAM disturbance, where accessing a DRAM cell disturbs other physically adjacent or nearby DRAM cells and exacerbate their charge leakage. So we organize DRAM cells in a chip in two-dimensional arrays of rows and columns, and we access them internally in a DRAM row granularly. So we want to access data stored in row 2. We need to first open row 2, and we can perform all our accesses to there. And once we're done and we want to access another row, we need to close this row. So if we perform this open-close operation many times, we observe bit flips in physically adjacent or nearby DRAM rows, leading to break of memory isolation. RowHammer is a primary example of DRAM read disturbance. Here, the row that we keep opening and closing or hammering is called aggressor row, and the rows that are affected as called victim rows. A simple way of avoiding bit flips is basically you perform an operation called refresh to the potential victim rows, and you avoid bit flips. But you need to do it before the bit flips occur, of course. With technology of scaling, DRAM cell size gets smaller in size, and they also get closer to each other. This exacerbates their interference, and in the literature, we see that the minimum hammer count needed to induce the first read disturbance bit flip reduces significantly in the last decade. This shows that DRAM cells become increasingly more vulnerable to read disturbance. With this background, my thesis identifies two problems. The first one is scalability with manufacturing technology. As DRAM cells become increasingly more vulnerable, prior works already show that existing solutions become prohibitively expensive or ineffective going forward, and therefore we need more efficient and scalable solutions to read disturbance. And we believe that we can achieve this by building a more detailed understanding of DRAM read disturbance. The second problem is compatibility with commodity DRAM chips. I'd like to take a step back and revisit how we access memory today. So in the application level, we use virtual memory addresses. And when we go to the system level, these virtual memory addresses are translated into physical memory addresses. And then in the memory control, we parse these physical memory addresses to identify which channel, which rank, which bank we need to go in the DRAM chip. All these translations are visible within the processor. And there is yet another address translation from processor visible row addresses to physical row addresses that happens inside the DRAM chip, and this information is proprietary. You do not have this information from the processor side. As a result, when a RowHammer attack hammers a row A in this example, processor-based defenses can easily identify this attack by observing the access patterns, and they can they can issue preventive refresh operations to addresses A+1 and A-1, but these rows can be in irrelevant physical locations, and bit flips still may occur in the actual victim rows. Unfortunately, prior solutions rely on this proprietary information. So with these two problem definitions, we conducted several studies, and they're published in several venues, and all of them are oriented around this thesis statement. We can mitigate DRAM read disturbance efficiently and scalably by first building a detailed understanding of DRAM read disturbance, And to this end, we looked into the effects of temperature, memory access patterns, victim cell's physical location, and voltage. Second, by leveraging insights into modern DRAM chips and memory controllers, we conducted some studies and proposed some mechanisms that leverage heterogeneity and parallelize parameter actions to reduce their performance overheads. And third, by devising novel solutions that do not require proprietary knowledge of DRAM chip internals, which we address by proposing another mechanism that selectively throttles unsafe accesses. So this is the list of my core contributions. At the same time, without further ado, I'll go with the first paper that's published in Micro. So in this study, we use the FPGA-based DRAM testing infrastructure. This program with a design called DRAM Blender, which is open source, and on GitHub you can just use it. We plug in a DRAM module to an FPGA board, and we have a PCA connection to the host machine to run the test routines and analyze the experimental data. And we have heater pads clamped together with the DRAM chips from both sides so that they can heat up the chips, and these are controlled by a temperature controller, and we have an external power supply that allows us to play with the voltage on certain power rails. This infrastructure provides us with fine-grained control over DRAM commands, timing parameters, temperature, and voltage. In the first study, we tested 272 DRAM chips from that implement two different DRAM standards from 4 major manufacturers. And here is the first set of analysis that we conducted. So we looked into the effects of temperature, and we observed that as you switch temperature from 50 degrees to 90 degrees, you have a lower bound and an upper bound in this temperature range. And in between these two bounds, the DRAM cell experiences bit flips, but outside of this bounds, it doesn't experience bit flips. So we call this range vulnerable temperature range. And when we look at the vulnerable temperature range across the chip, we observe that there is a significant variation in vulnerable temperature range across different DRAM cells. And most cells are vulnerable to disturbance in a continuous temperature range. These observations led to have some immediate implications. An example on testing is that now you need to test your DRAM cells at every possible operating temperature to accurately measure their vulnerability level. Another example implication on defenses is that you can choose to retire some cells based on their temperature, based on system temperature and their vulnerable temperature range. And another implication of attacks that turned out to be a follow-up work from other people that basically uses temperature sensitivity as a side channel to conduct a system level attack to spy on temperature. The second key finding is about the access patterns. In particular, we look at the accuracy of on time. Before our study, the worst case known access pattern was to open and close DRAM rows as frequently as possible with the minimum delays in between activations. Now what we do here is that once we open a row, we keep it open for some time longer than the minimum allowed time. And by doing so, we observe that we can significantly reduce the number of hammers or activations that is needed to induce the first bit flip. And this has also immediate implication on the defenses. If your existing deployed mitigation mechanism is not accounting for this particular effect, that you can bypass it by changing your access pattern. And this finding also turned out to be some other folks follow up on this work, and then they released last year the discovery of a new DRAM disturbance phenomenon called RowHammer. The third key finding is about the variation across rows. Let's say that this box here represents all your DRAM rows in a DRAM bank. We observe that if you need n hammer count, n hammers to induce the first bit flip in the weakest 10% of the rows, you need at least double of that hammer count to induce bit flips in the remaining 90% of the rows. So this shows that RowHammer vulnerability significantly varies across DRAM rows, and this also has an implication on defenses. If you configure your solution for the worst case row, then you end up overprotecting many rows, and it makes your mechanism more expensive unnecessarily. And this also has a follow-up work that is part of my thesis this time, and I will cover it shortly. So the next paper about building a detailed understanding of DRAM disturbance is focusing on the effects of voltage, and it's published in DSM. So here, a closer look into the DRAM disturbance is like when we conduct a RowHammer attack, basically open and close aggressive rows many times, right? So high voltage, low voltage, we drive the Wordline with high voltage and low voltage. And repeatedly turning the Wordline voltage is a key thing to lead to RowHammer bit flips. So when we look at effects of reducing Wordline voltage, we expect that it can reduce RowHammer vulnerability, and it can come at the cost of having cells in a weaker state. In this study, we also tested 272 DDR4 DRAM chips from 3 major manufacturers, and we observed that as we reduce Wordline voltage from right to left here, we look at the bit error rate caused by the read disturbance, and we observe that it significantly reduces. So basically, the key takeaway is that fewer DRAM cells experience RowHammer bit flips under reduced Wordline voltage. Similarly, when we look at the minimum hammer count to induce the first bit flip, or as known as RowHammer threshold, we show that as you reduce Wordline voltage, you need higher hammer counts to induce a bit flip. So basically, reducing Wordline voltage reduces RowHammer vulnerability in that sense. We also looked into the other effects of reducing Wordline voltage on DRAM, in particular row activation latency and data retention time. And in both these studies, we showed that for most of the DRAM cells, you have already very large safety margins, or as known as dark bands, that allow you to just use nominal parameters to make them reliably work. But for the small fraction that exhibit erroneous behavior, you can also play with the time parameters a little bit, or you can enable singular recursion ECC to avoid bit flips. And with this finding, I'm done with the building and detailed understanding of DRAM disturbance. The next step, of course, are leveraging insights into modern DRAM chips and memory controllers. And in particular, we leverage heterogeneity in this paper. In this paper, we test 144 DDR4 DRAM chips from 3 major manufacturers. Now we test on rows in 4 different DRAM lines. And we observe there is a significant and irregular variation across DRAM rows in terms of their disturbance vulnerability. And current solutions are configured for the worst case, and they overprotect many rows into large performance sockets. And our key idea is to dynamically tune the aggressiveness of an existing solution to the victim row's read disturbance vulnerability. Our mechanism basically performs fewer preventive actions, such as refreshes, for stronger rows, so that the performance overheads are reduced. Here we integrate this mechanism with several existing solutions. Here's an example of HiRA. When a row activation happens, HiRA generates a random number. This is a prior work that is compared against a threshold. And if the random number is larger than the threshold, then the parameter refresh happens. So basically, we provide this victim row information to our mechanism, and it dynamically changes the threshold value so that if the row is less vulnerable, it applies a higher threshold, leading to fewer refresh operations, and vice versa. So our mechanism works with many read disturbance solutions, and we show it for 4 state-of-the-art recent ones. I obfuscated one of them for blindness reasons. We evaluate the performance effect of our mechanism here, and then we show that it reduces the performance overhead of existing solutions drastically and significantly improves system throughput by doing so. And we look at the hardware complexity as well. We show that it incurs no additional latency to the DRAM accesses, and it can be implemented in low cost. Second work is parallelizing preventive actions. Here we leverage the key insight that compared to activating 2 rows in a DRAM bank, can lead to, if these rows are located in 2 different subarrays, we can refresh 1 row while concurrently opening the other row. We show that this operation works on 56 off-the-shelf DRAM chips from SK Hynix and SK Hynix only. And it reduces the time spent for refresh operations roughly by half. And we can effectively reduce the time spent for refresh operations on off-the-shelf DRAM chips by doing so. So based on this observation, we propose a new mechanism in the memory controller that generates periodic and RowHammer preventive refresh operations with a deadline. and buffers them until their deadline and finds opportunities to perform them in parallel. We look at the performance impact of this mechanism and show that it can significantly increase the system throughput by reducing time spent for preventive and periodic refresh operations. And we also look at the hardware complexity and show that it can be implemented at low cost and with no additional latency to memory accesses. The last part of the work is addressing the second problem that I mentioned about the address translations and this proprietary information. So when a RowHammer attacker hammers a row, we do not know which row addresses actually correspond to these actual victim rows. So what we propose is that we detect hammered rows using area-efficient blow filters, and we selectively throttle the accesses targeting these hammered rows, so that we do not need actually this victim row address, because we already make sure that this particular row is not activated enough number of times to induce bit flips. And by doing so, we prevent disturbance bit flips without knowledge of or modifications to DRAM chips. We evaluate this mechanism against 14 mechanisms of the time in terms of comprehensive protection, compatibility with commodity DRAM chips, scalability with worsened RowHammer vulnerability, and deterministic protection. And we show that ours is the only mechanism that satisfies all four properties. And we also compare the hardware complexity and show that our mechanism is low cost and competitive with the other mechanisms. When we look at the performance evaluation, we show that our mechanism incurs negligible performance and energy overheads when there is no attack going on in the system. And when there is an attack, what we do is basically throttle the accesses of the attack, so it slows down the attack a lot. That opens up some memory bandwidth for the concurrently running benign applications, and by doing so, it can improve the system throughput and improve the energy efficiency as well. So this concludes all the contributions in my thesis. Beyond these, I had the chance to collaborate with many people in our group and work on different topics, all oriented around computer architecture and hardware security, and published several papers in different venues. Going forward, I believe that we need even a deeper understanding of physics and vulnerabilities of the disturbance and other vulnerabilities as well. And for that, we need to understand better how DRAM ages, and we need to come up with better online profiling methods that gives us that works faster and more efficient. And we also need more investment on flexible and intelligent memory chips, interfaces, and controllers. There are multiple topics here. I'm not going to go over them, but I'm happy to talk about them in the coffee break or in the Q&A session as well. And we need better cross-layer communication, hardware, software co-design to detect an ongoing attack or bit flips more accurately in a faster way, and also mitigate the problem in edit source in the system level. We already have some ongoing works currently, and I hope to share them with the community soon. So I had the pleasure of part of my works get recognized by the community, computer architecture and hardware security community, both in academia and industry. And I want to thank you for giving the opportunity to share these results in this competition. And I have a lot of people to thank, but I cannot name them here, so I'm just going to show this and conclude my presentation. And thank you very much. I'm happy to answer your questions. Yes, it's an ongoing research problem actually. You really need to rigorously test whatever DRAM chip you have at the moment. There is a large variation caused by just like random manufacturing process variation. Then we also observe some impact on design-induced variations as well. When we look at the vulnerability, so for example, you look at some columns that are vulnerable to RowHammer, and you compare them across different chips in the same module, and you observe that the same column is vulnerable across all chips. So it actually suggests that there is some design-induced variation as well, but it's really like the minor part of the variation. The majority is really it just looks random. We couldn't detect any pattern. So we believe that it's due to the manufacturing process variation. So it requires really rigorous testing for any given chip.
Thank you. So I have a question.
Sure.
So I wonder if there are any real-world damages, accidents, or security events in the industry caused by the RowHammer.
So I can say that industry is obviously working on this. So there are like, if you just like follow the new specs, starting from like DDR4's updates to DDR5 and so on, you see that there's more effort in the standards from JEDEC as well that pushes this mitigation mechanisms and so on. And it actually shows that there is some worry about that in the industry as well. And so, for example, there is this upcoming paper, again, not my paper, so I can't really show the author names. So that shows like even in DDR5 today that it's supposed to be like RowHammer free, you can actually achieve the tulips. So I'm not aware of any like articles that says that, oh, this many devices are hacked already using RowHammer. Probably attackers are using simpler methods now, like phishing attacks or things like that. But the vulnerability exists still at the system level.